So the first thing we're going to want to do is draw the relationship between Kerma and absorbed dose in water. Then discuss what relationship must exist and adjust the graph if charge particle equilibrium actually existed. So first and foremost, we need to draw a absorbed dose, just a depth dose curve. You should be very accustomed to doing this on the fly very easily. So we're going to have our buildup region, and then we're going to have our fall off due to scatter and attenuation. Then now we need to draw our Kerma. So here I'll do it in dotted lines. So the relationship here is in fact important. So for D max, which I'm going to say is right here, that is where charge particle equilibrium actually is met. That is where Kerma and our absorbed dose is in fact going to match. Now, the rest of the Kerma line is simply a downward slope with the same slope, so the same rate of decrease. So the Kerma, which is this dotted line here, is going to actually be higher than absorbed dose in the buildup region. And then once we hit D max and we start to go into our scatter and attenuation, the Kerma is going to actually be less than that of the absorbed dose. So what's happening here is high energy photons are entering the water, the patient, whatever you may consider, and then those high energy electrons are ejected from the surface and they deposit energy until they are stopped, which is why we have this buildup region. And obviously that is going to cause secondary interactions, ultimately add more and more dose deeper into the tissue. This obviously increases until we are at a max point, and then that is really when your scatter and your attenuation take over, and that's when your dose starts to decrease. So this relationship between Kerma and absorbed dose is really based on transient charge particle equilibrium. And it's transient, not full charge particle equilibrium, because of the scattering, the attenuation, the forward scatter of the electrons. I'm just going to put TCPE right here. And that doesn't lead to full charge particle equilibrium. What that essentially means realistically is that the TCPE is going to lead to a proportionality between dose and Kerma. And normally that's given with a beta. So the beta, for example, is just the relationship between the Kerma absorbed dose. So in the buildup region, beta is going to be greater than 1. Afterward, beta is going to be less than 1. And so transient charge particle equilibrium, that's what we have in real life. That is what we treat with. Now, if theoretically, hypothetically, somehow we had fully charged particle equilibrium, what would that look like? So I'm going to draw a separate graph just to make it a little easier on us. There was not too much stuff being written down. So if there was full charged particle equilibrium, what would happen is our absorbed dose would still have a buildup region, but then attenuation and scatter wouldn't exist, so you're not losing any dose. That same amount of Dmax dose would be throughout, regardless of the depth of your water, your patient. And then what would happen here is specifically our collisional Kerma would meet this absorbed dose line. Now, there wouldn't be a buildup region, just like there isn't normally for regular Kerma there, but it's going to be at that same level of Dmax, and it also is going to be a horizontal line. Typically, the ratio for going back to the TCPE is 1.02 is the ratio from dose to Kerma on average there. So that gives you the relationship between these two. If you have questions, please comment below. Happy studying. Keep at it.